Our final speaker is Boyd Platt. Boyd is trained as an architect, and he is the founder and CEO of Branch Technology, which is, as I think you've heard, a 3D printing company. So he will speak to us today about 3D printing and its potential to revolutionize design in building and construction. Okay, you're on.
Thank you. Branch has combined 3D printing with conventional construction materials to enable a new way to construct buildings that explode design possibilities. I'm Platt Boyd. I'm an architect and practiced for 15 years before leaving that about 3 years ago to begin Branch. And the fundamental question that we're asking is, what if you could build like nature? So in this, what I'd like to do, well, first is ask a couple questions. One, who here is familiar with 3D printing, traditional 3D printing? And then one follow-up question to that, how old do you think 3D printing technology is? So if it is 3 years old, keep your hand, well, if it's 3 years old, please raise your hand. 5, 8, 10, 15, 25, 30 years old. It's about 30 years old. So it's been around for quite some time. It began in 1984, was when the first patents were filed. And this is something, there's a couple fundamental technologies, and I'll go over those real quick. So one is FDM, Fused Deposition Modeling. It's taking an object, imagine a coffee cup, and slicing that into 1,000 layers horizontally, and then building that up layer by layer, as you see here, with a small nozzle that's extruding plastic out in layers. And then in the end, what you get is what was 3D modeled in a CAD program, then you see that in reality. And in this case, it's fused plastic. Second one is kind of like laser printing with a photopolymer. And so it's a vat of photopolymer that it laser hardens a layer, and then that sinks down into the photopolymer, and then at the end it rises up with that end-use part that is then cured through UV exposure, and then you're left with that part that you modeled. And so all of those use 3D modeling and the typical CAD programs that a lot of the designers that you're familiar with use. So when you begin to scale that up to construction scale, there's a couple entities out there in the world that are pursuing this. One is Enrico Dini and D-Shape in Italy, and it's a similar technology. It's called powder bed, and so they use a sandstone material. They make a gantry over this, and then they lay down a polymer in that solidifies, and then another layer of sandstone, and then more polymer. And so in the end, they evacuate that entire chamber, and then what you're left with is those parts that are hardened. Another is Deuce Architects in Amsterdam, and they make, it's a huge maker bot, basically, and it's something that prints with plastic, and then they make bricks, and they Lego those together in the end to make a building. And then the third is Contour Crafting, a professor from University of Southern California that builds a big gantry crane mechanism and lays down layers of concrete over time. And so all of these have some commonalities. They're all layer by layer built up slowly over time using exclusively the 3D printed material, whether that's concrete, plastic, or sandstone material, and they have to build something larger than the thing that they're constructing. So it was through some of these things that really inspired Branch and the idea behind Branch. So why would you use 3D printing? One, this is on the small scale, because manufacturing complexity is basically free. So the filigreed nature of this piece that you see right here, the volume of that versus the volume of a cube of material is the same price. It's just based on the volume of material used. And if anybody is familiar with parametric design and some of the tools that are available, they can customize things very, very easily. And so that customization through 3D printing is, again, virtually free. It is a direct digital fabrication process that translates from the 3D model directly to the built thing, rather than having to go through paper plans and specifications and then the interpretation of those paper plans and specifications by subcontractors and general contractors. It's direct digital fabrication. And when 3D printing has been studied on the small scale, you can save up to 50% of the material to make an object and over 50% of the embodied energy to make that same object. So that's why 3D printing is interesting. One other entity that is pursuing large-scale 3D printing is Oak Ridge National Labs. And so this was me about a year and a half, almost 2 years ago, geeking out in their lab. I said, "There's the car, can I sit in it?" And they let us sit in it. And so that was a car that they 3D printed in collaboration with Local Motors. This was the second car that they did. So it's a really sexy car. It's a Shelby Cobra. This one, they printed it in layers, then they milled it down through a CNC process. And then there's a lot of Bondo and elbow grease to make this look like that. But President Obama and Biden came to the unveiling of this in Oak Ridge, Tennessee about a year and a half ago. Another pursuit that they've done is with SOM. This is, again, layered printing to produce a small trailer. This was parts that were printed and then bound together with compression rods to show what's possible when you begin to scale this up. So what we're doing is a bit different. We've called it CFAB, or cellular fabrication, because that's where it takes its cues, is looking at the natural world. So what we have is freeform 3D printing, where we've utilized our hardware and our software that we've developed to solidify material in open space, and then it builds a matrix like what you see here. This is something that is the same volumetric speed as the fastest and largest 3D printer in the world at Oak Ridge National Labs, but it's 165 times less material. So our algorithms create the internal geometry and drive the robot in almost any configuration. And this is utilizing carbon fiber reinforced ABS plastic, which has over a 1,500 to 1 strength to weight ratio. This is another example of that. This is glass fiber reinforced ABS. That a piece that weighed about 2 pounds could support 3,000 pounds in compression. So we use that as the starting point. For the addition of conventional construction materials, starting with spray foam and then concrete, and then you can finish that in various ways on the interior with gypsum, on the exterior with stucco, brick, siding, fiberglass, what have you, so that what you end up with is a composite assembly in the end. And so the mindset behind this is prefabrication. And so we prefabricate wall panels in our facility. Right now, we have the largest freeform 3D printer in the world. It's a 12.5-foot robotic arm on a 33-foot track, giving it a print envelope of 25 feet wide by 58 feet long. We just brought our second one on last week, and we're looking to bring our third one on this week. But what we do is we prefabricate wall panels in that envelope and ship those to a job site, fit them together like big Legos on site, and then you can begin to route utilities through that, and then begin adding those traditional construction materials into that so that it can become a custom composite that when we've tested that with just the spray foam, something like this that has the matrix plus spray foam, something that weighed 28 ounces, held up 6,000 pounds. That's about 3 times the strength of wood stud construction, and that doesn't even include the concrete yet. So what we've begun to do while we're going through some testing for load-bearing assemblies is do interior and more decorative components for ceilings or wall assemblies, wall panels like this, ceiling assembly like this that is a groin, example of a groin vault like in a cathedral. This was a project that was about a year ago we did for the Museum of Design in Atlanta. It's the tallest 3D printed object in the US at 18 feet tall, and we worked with the architect that designed the 9/11 memorial for the Pentagon on this, Keith Caseman. Another example was the topography. We're based in Chattanooga, Tennessee. This is the topography of the Tennessee River Gorge across 4 different acoustical panels in an innovation center in Chattanooga. Architect entered a design competition for a children's playhouse in Nashville. They won that competition based on our capabilities. This was a small children's play pavilion that we did in the Botanical Garden in Nashville. And this is another one of those very interesting architect projects that is drone based, and this is a drone landing pad that will be located in Knoxville. It's our second project with Keith Caseman, and he'll hang that on the side of a building in downtown Knoxville. Beginning to look into tensile properties of like beam treatments. And so this was earlier this year, looking at how it performs in tension. If you look at our website, branch.technology, on the leadership page, you'll see the same beam, and there's 6 people sitting on that same beam. We have an early collaboration with MIT right now looking at how you begin to optimize the internal geometry within a beam, or in this case, a cantilever state. And the base case is example on the far left, and that's our traditional matrix, and then different ways to optimize the internal geometry within that matrix. And then the fourth one over that looks kind of like an iso grid is similar to a Mitchell truss, and that's something that is 1/5 of the internal strain within each of the members, same loading case, but far less material used to create that. So if you're familiar with parametric design or Revit or Grasshopper, Dynamo, some of those programs that are out there in the design world, you can create one script in red, and then you can adjust sliders or variables within that and create endless variations. So all of these different pieces that are beyond that red one were one script, but just people customizing that for what they wanted to see out of that, whether that's the height, the curvature, the twist in this. It's something that you can create almost endless variation, which is enabled through 3D printing. And so one of the things that we began a local launch in Chattanooga a couple weeks ago was to look at furniture and how we could use that to highlight a use case. The top 2 groupings are both parametric, where they can be adjusted. It's the same script, but different variables have been adjusted to create something that's a table height versus a seating height. We've also begun looking into other materials. So this is ABS that we've been primarily working in. In this case, this was one of the pieces of furniture printed in a biopolymer that's sugarcane based and is a polyethylene rather than it being an ABS. It smells like vanilla when you print it. So that's a little bit better than ABS. So these are a couple other pieces that we did that were one-off pieces from a designer, one that went to New York and another that went to Nashville. So the thing that we're very, very excited with right now is a project that we're printing currently that will debut in a couple weeks for Design Miami. We're working with Shop Architects out of New York, and this is the project that it's 2 pavilions. They themed this after a sea creature. So it will be in one location in Miami for 5 days, associated with Art Basel, and then it'll move to another location for 2 years down in Miami. This is another one that we're collaborating with Oak Ridge National Labs. They're producing the more solid parts that you see towards the bottom of the slide. And how we produce that, so this is the parting, the panelization diagram, and so the middle part is the whole thing, and then how we begin to divide that up and print the different pieces. And to give a sense of scale, this is one of those parts. So it's about, I think this piece was about 24 feet long by about 6.5 feet tall. But very lightweight. A couple people can pick that up and move it around. And so that's one advantage of this is you could build large panels, and instead of having to crane them in place, a couple people can take those and put them and install them on site. So the commonality with all of those projects is it's the same algorithm that creates that and drives the robot, but it is almost endless variation. And so if it were a straight wall or one with double curvature, it's the same price. It's based on the volume of that object. And so we can take files from almost any CAD program, whether that's Revit, AutoCAD, Rhino, CATIA, pretty much anything people have given to us, and we can use that. So why would you pursue 3D printing in construction? That's kind of a fundamental question. It's because every building out there is unique, but the way that we've been producing those is by taking commodity and homogeneous components, taking those to that job site, and then customizing them on the site by cutting and carving out of that, and then typically throwing away all the excess. In the commercial and residential construction industries, that creates $30 billion of construction waste that has been harvested, transported, post-processed, and then taken to a job site and then discarded. So that's an enormous amount of waste. And there's been studies that have shown that the construction industry is something that is decreasing in productivity over time. The other thing, as an architect, typically the budgets that we're given constrain us to making cookie cutter boxes, which is not the most satisfying thing as an architect. We like to be a little bit more creative. And then the complexity of the paper coordination process creates a lot of errors and omissions in our industry. Customization is also typically very costly, and so that creates a big, big problem. An interesting thing is, as we've gone out and raised venture capital funding, there's not a lot of interest from the venture capital community in the construction market. And that's really, to me, is insane because it's 8 to 10% of GDP. So why wouldn't they be interested in innovating in the construction industry? It's almost like an oxymoron. But it's an incredible opportunity. It's about just quantifying those things, it's about a $125 billion opportunity or problem in the construction arena. So what's the solution? Well, of course it's 3D printing, but not really. But it can begin to address, in part, some of those inefficiencies. And so a prefabrication process is something that has been shown to be it's a factory process. It's about 1.7 times more efficient than an on-site fabrication process. And it's something that the component framed industry has studied this, and it shows that when you prefabricate components in the quality controlled environment, and then you can use only the materials really that are necessary, it can waste 1/30 of the materials used typically on an on-site construction process. So it's very efficient. And so the basic premise of what we're doing is it's democratized design freedom. It's kind of taking that Frank Gehry, Zaha Hadid, Calatrava level of design that's $800 to $1,000 a square foot and allowing a broader set of designers and architects to have that in the $200 square foot construction budget. So one of the first things that we wanted to do was demonstrate this and show what this can be done with load-bearing conditions. So we sponsored a design competition. We had over 1,300 registrations from 97 different countries shown here. The winner was published all over in over 150 million monthly readership publications. And then the variety of entries that came in, we culled that down to the top 50 and allowed people to vote on those on our website. And so there was entries that were coming from different design approaches. We gave our capabilities out, and each of the designers came up with their interpretation of what would be an appropriate example. And so some that were very biomorphic or biomimetic that take a tortoise shell and literally mimic that. And the time and effort that went into this really blew us away. And at that point, we were a 5-person startup. So to have the ability to reach a very broad audience was really, we were very excited about it. So these are some of the examples of what people came up with. So giving it out for online voting, this was the People's Choice Award, a very simple concept of a folded leaf. A group out of Romania won this. We had SOM, Big, Thornton Tomasetti from a structural engineering standpoint, Jessica Rosencrans with nervous systems, and Keith Caseman, who we had collaborated with on a couple projects, was our design jury. They voted this one as the Visionary Design Award, meaning that it was amazing design, but there's no way we're gonna construct that. It was all these little windows. It would cost a fortune and most likely leak. So we didn't want that to be our first example of a project. The winner, though, was WATG, which they're a global hospitality design firm, I think ranked number 2 in the world, and their Chicago office designed this. And it is going towards our ultimate goal, which is load-bearing construction. Example projects being residential or facades for commercial buildings. And so we gave our capabilities out, and this was definitely pushing the envelope of what is possible with 3D printed construction. But the interesting thing is this was working within our given capabilities, and this is a lot easier than the project that we're doing with Shop right now. Structurally, we actually, on this, didn't think that this was possible. But Thornton Tomasetti, the structural engineer, said this was their favorite because it was based on arches. So the entire structure was fairly short-spanned arches. It was a simple program, 1 bedroom, 1 bath, kitchen and living area, meant primarily to demonstrate what's possible through 3D printing, and the renderings and the design on this blew us away. It's a beautiful design, and so what we're going through right now, we've received National Science Foundation funding to pay for the ASTM testing for load-bearing assemblies, ASTM E72, and we will be going through that over the coming months. Once we get those results back, we will use that to engineer the walls in the building, and then we'll construct this next year as our first demonstration project of a load-bearing capabilities. And Here you see the simple structure. So it's arches that are bound around the programmatic spaces, and then putting a second arch on top of that so that it becomes a double-arched structure. And then that will be panelized and then assembled on site. So the idea behind this is looking at how things are made in the natural world on a cellular basis. So the bounds of a cell create some strength, but it's really the material filling those cells that provides the majority of the strength and function. So in our muscles, it's blood and water pressure. In a tree, it's turgor pressure, which is water again. In a bone, it's calcification. So what we're doing is using 3D printing to create that complex outer geometry, but then using the economical construction materials to become the strength and function for a normal wall assembly. And so it's just at the very beginning of translating the ultimate efficiency, the beauty, and the strength that you see in the natural world into how we can construct buildings. And so just taking those first small steps towards that. And so here you see, if any of you had statics or strengths of materials back in college, a moment diagram on the bottom, and a beam at the top that's efficient, meaning that it's only using the material necessary to create that span. And so it's much more efficient than the conventional beam that you see up top, that's just an I-beam. And so what this begins to do is it opens up a new way of thinking about what is possible in design. And it's saying, do we have to do homogeneous wall thickness? Do we have to do beams that are all the same? And it's looking at being shape efficient and using only the material necessary. So it's about stewardship of resources. It's about enhanced productivity, going from a digital to a direct end result. And ultimately, what's very satisfying for me as an architect is it's democratized design freedom, allowing a much broader audience, people of what I used to practice, to have access to greater design flexibility. So that's all I've got. There's a second session tomorrow called Surfing the Mavericks, where it'll be open to Q&A. I welcome any of your questions or interactions. The main question is, what would you make if you could build like nature? Thank you.